Hello and welcome to Knowledge Talks with me, Simon Singh. We humans like to think of ourselves as the most intelligent beings on Earth. We pride ourselves on our ability to have abstract thoughts, to be creative, to feel deep emotion. But will we always enjoy this exalted position? In 1950, when computers with the power of a wristwatch occupied the space of a large room, Alan Turing, mathematician, codebreaker and computer pioneer, predicted that by 2001 we would be quite used to having thinking machines all around us. Well, today genuine artificial intelligence, or AI, still seems a long way off, but Turing's dream has not been forgotten. That clip from the new Spielberg film AI is set in the late 21st century and paints a rather ambitious picture of AI. But is AI really achievable? When, if ever, will we have genuinely intelligent machines, and how far have we progressed so far? Is AI even desirable? To discuss these and other issues involving artificial intelligence, I'm joined by 4 members of the Artificial Intelligentsia. With me here at the Welcome Wing at the Science Museum, I have David Stork, the Chief Scientist at RICO Innovations and Consulting Professor at Stanford University, Kerstin Dautenhahn, Lecturer at the University of Hertfordshire's Department of Computer Science, Mark Bishop, Lecturer in Cybernetics at the University of Reading, and Bill Phillips, Cognitive Neuroscientist from the University of Stirling. Now, I know we have some diverse opinions here on artificial intelligence, but perhaps we can start by agreeing on what it is we're striving for. What is intelligence? What would we expect an intelligent machine to be able to do? Mark, perhaps I can start with you.
Well, I don't think intelligence is any one distinctive feature. I think it's probably present in lots of systems, and for me it increases perhaps with the ability for systems to interact with an ever-increasing and ever more complex environment. It's not just the complexity of the environment and the system's interrelations that matter, it's the flexibility of how that system interrelates with the environment. So that's one kind of operational view of intelligence that seems useful to me in my work as an engineer. But a second, more human part of intelligence for me is the, you might call, the relating ability of the mind, the ability of the mind to see whole. If you consider all the sense data that's coming in through our senses, the ability of our brain to unify that into one common view of the world, what Kant called the unity of apperception.
Bill, you're our sort of brain expert. What is it that the brain does that makes us think it's intelligent?
Well, different psychologists will give you plenty of different answers. As far as I see intelligence, it's a concept invented to summarize something that's far too complex to be characterized by a single word or a single measure. All of the sciences that study the mind make it absolutely clear that mental processes involve many specialist subsystems. For example, in humans, there's the verbal, spatial, musical, emotional, social, and each of those is itself a mass of interacting subsystems. And also, a lot is known about how these develop, what the specializations are, and a lot about how they're implemented within the brain. But what isn't yet understood is how all of these specialized activities are dynamically coordinated to produce novel outcomes in novel situations. And that is part of what a lot of people think of when they talk about intelligence.
So it's not the individual strands of intelligence, but also the way you can combine them.
Normal intelligence test measures both knowledge and its novel use.
Kerstin, is there anything to add to the list that we've missed?
Well, certainly when something like social intelligence was mentioned, this is something I am interested in, because I would criticize that artificial intelligence research has always very much focused on what human intelligence is and why humans are different from other animals. I like, for instance, to talk to people who study non-human animals and try to find out about the origins of intelligence. And one of the fascinating hypotheses is, for instance, that the evolutionary origins of human intelligence is in the ancestors of human beings learning about how to deal with other fellow creatures, with other human beings. So that social intelligence is a primary and crucial factor in the evolution of human intelligence. And going back to an AI perspective, it is a very interesting and huge challenge to build systems that are socially intelligent, that can interact with human beings or with each other.
Well, social intelligence is certainly something we want to come back to. David, perhaps I can just slightly rephrase the question. I know you're a big fan of Stanley Kubrick. Stanley Kubrick came up with the idea of the Spielberg film and saw it through to his death at least. He also came up with 2001, the film. In that we have HAL, which is a wonderful example of artificial intelligence. What is it that HAL exhibits that make us think that HAL is more than just a 20th century computer?
Well, it's been said that artificial intelligence is making computers do what they do in the movies. And Kubrick is a perfect example of that. Not only did he have HAL, but as you say, David, the young boy in AI, HAL could speak, reason, lip read, had emotions, reason, had a sense of self, could tell the emotions in the crew. I can see you're upset about this, Dave, and so forth. He exhibited a wide range of abilities that we partake and say is part and parcel of being intelligent.
He pretty much picks up on all the points that we've made so far. Okay. Well, that's what we think intelligence is, what we expect artificial intelligence to show. But the question is, where are we today? We asked technology strategist Peter Cochrane what his views were.
AI, or artificial intelligence, is an intelligence created by humans and not by nature. The difficulty we have is there is no adequate description, quantification, or measure of intelligence, and so it's couched in words, and it's very fuzzy. Most of the definitions and the visions that I see of AI are related to the anthropomorphization of technology. It looks like us, and so it's scary. Really, that's not what it's about at all. AI is really about creating machines that will do jobs and work for us that will allow us to offload the menial and expand our capability. Ordinary computer programs are purely logic. They're entirely algorithmic. You put in an input, the output is always the same. An AI system, on the other hand, will learn. It has an element of cognition. It takes in an input, it compares it to behaviors and outcomes from the past, and it changes the output accordingly. In principle, my laptop computer could be smarter than the average rodent. If we ask the question, why isn't it? It comes down to some very simple factors. First of all, the input to that machine is very limited, a keyboard. The output, on the other hand, is very high, a screen. The processor is fixed and the software is fixed. Now, in the rodent, everything is reversed. The input is very high, ears and eyes. The output, movement, is very little, and the hardware, the brain and the software, the algorithms, if you like, inside the brain, are all adaptable. We've now reached a point where we can make the software and the hardware adaptable in our machines, and we can give the machines huge amounts of input. So in principle, we stand at the very verge of creating very intelligent machines.
One of the points I noticed that Peter Cochrane made was that the wonderful thing about rats is that they have very rich inputs. They can see things, they can hear things, they can touch things. They're continually being stimulated. Whereas my laptop at home, I type it occasionally, I click my mouse, I get a bit of modem input. Is that a significant point? Is that really a barrier to achieving artificial intelligence? David?
Well, some people feel that we need embodied intelligence, having physical devices, robots that interact with the world very richly. And then later you could use them through a very narrow channel, like text, once it's somehow, many, many years from now, experienced enough in the real world, then you could ask it questions. I think that the importance of data is crucial. We need lots and lots of data, that it's just too difficult to try to program in and understand exactly what is language, what is vision, and so forth. And so most of us, I think, are of the viewpoint that training systems, giving it lots of examples, is crucial, and getting rich environment is important for that.
So I think that's something that you've worked on, Kerstin, isn't it? having robots that actually have an existence and a life in which they can accumulate these experiences.
Yeah. I mean, one of the issues which I'm not sure how Peter Cockman actually meant that, but one can get the impression that he wanted to advocate that more is better, and which means if you have more sensor information, if you have more actuators, and if you have more memory power, then automatically, or more or less, things will get better. We will have more complex systems, more intelligent systems.
But our computers are doubling in speed every year. So what he's saying is that we will eventually get there. We'll have the power to achieve these things. It's as simple as that.
But what do you do with this computing power? This is the really, really crucial question. You can do fantastic AI research with a very slow computer, with a very old robot. How to use sensor information, how to translate in a simplified way, but how to generate motion, behavior, speech. This is still very, very much unsolved problem. I mean, computing power, memory space, price of hardware. This is certainly something that will help, but
Bill,
it will not solve problems.
I mean, does the brain give us some idea of how powerful is the brain, and how does it deal with all of this data?
I mean, at a very simple level, it's very clear that primate brains and most mammalian brains all mammalian brains probably, are very huge. In the human, it's a well-known statement, 10,000 million neurons, on each of which there will be something like 100,000 ion channels, which at their fastest rate of operation can open and close 1,000 times a second.
So those are connections between...
The ion channels are what implement the synaptic connections between the cells. So if you multiply all those numbers up, you are getting to very big numbers. From a psychological point of view, we know that we are using a vast amount of knowledge. We have a lot. We acquire knowledge and we're using it. And that the knowledge that we use at any moment, although it's a lot of knowledge, is a small subset of the amount that we have stored. So that the way of selecting a large subset from a much bigger body of knowledge appropriate to the circumstance is a really challenging task, and we can be confident will require a lot of computing power.
Yes, another way to say her point though is we have the compute power to implement a fly's visual system, and we don't know how to do it. Absolutely. We cannot duplicate a fly's ability to recognize simple objects. So it's not just compute power, I think.
Because the fly, as it grows up, it develops a huge body of knowledge, and then once you have this huge body of knowledge, you have the problem of trying to pick out the right bits, which is okay. Absolutely. Today, with AI systems that we have, or so-called AI systems that we have, what are the highlights? I mean, imagine you've got a sort of an artificial intelligence version of Desert Island Discs, and you're having to take something away with you to remind you of what great achievements AI had at the turn of the century. What would you take away as your favourite bits and pieces?
I think for me the Honda P3 robot, bipedal robot's got to be up there. It's a truly amazing piece of technology.
What does it do?
Well, for one thing, it can play football.
Right.
It can
so you're talking about something that looks like the bottom half of a human.
It looks like a whole human. It's got a back. Looks like a human in a spacesuit. And this robot can walk upstairs, walk downstairs. It can kick a football around. At the moment, the Honda is still aware that they need to spend more time on the software for this phenomenal piece of engineering, because a lot of the robot is still controlled offline, and they'd like to give the robot much more intelligence. But nonetheless, as a piece of AI embedded hardware, I feel that the P3 is one toy I'd like to take away with the Desert Island.
Play football with it. So it's a machine that can walk, but it couldn't walk if it had to carry its own brain, because the offline stuff is just too big and too heavy.
Yeah, at the moment they haven't got the AI side of the software, if you like, sorted as well as they might do.
I would point out Deep Blue, not because it's intelligent.
Deep Blue is
the IBM's computer that beat Garry Kasparov in tournament play in 1997. It did so by not emulating how humans play chess. Human masters especially look and see patterns and structure in the pieces on the board. Instead, Deep Blue used massive parallel search to explore lots of dumb moves, but in order to find the good ones. Even its creators agree this is not an intelligent system. It has no generality, it can't even play checkers and so forth. But what it did show is that you can solve a problem that people thought was particularly difficult in a way that's very unlike the way humans do it. And I think we're going to have to get used to the notion that ours is not the only way of solving some of these hard problems. And so that would be on my list.
But did Deep Blue realise that that it had won a game of chess?
No, absolutely not. No, it is not intelligent, had no sense of self, it had no pride at winning. Nevertheless, it solved a well-defined problem that people have, put forth as a difficult one in a way that's not intelligent.
And when you say Deep Blue beat Kasparov, do you mean that the physical machine, or would it not be more correct to say the team of designers at IBM, in conjunction with some very fast hardware, as a team beat Garry Kasparov?
Sure, but I think you'll get that with every AI system. You're building anything that, engineers and scientists build, you could always point to and say, well, look, they put the hardware together that learned how to crawl across the building. Look, across the floor. So you're always going to have.
But it's a bit different.
That's what we meant by the artificial intelligence.
All of these machines seem to exhibit some level of intelligence, but they are limited. So can we go further? What is the ultimate challenge of AI? Well, computer pioneer Alan Turing came up with a test which he thought would tell us when we've achieved true artificial intelligence. Here's his biographer, Andrew Hodges, to tell us about Alan Turing's views on thinking machines.
For Alan Turing, the puzzle of the mind was there right from the beginning. The story of computers is often told as a story of objects built by engineers on which other people then ran programs, and then other people came along and said, let's see if we can make the programs into something like intelligence. But the thought processes in Turing's case really went the other way around. It's the nature of thought which comes first. But in 1936, when he was thinking about this, no one would have guessed what it was going to lead to in a mere 10 years or so. What, of course, changed the situation completely was the advent of the Second World War and the fact that Alan Turing came into the immensely important business of breaking the German military and naval codes. And that was the thing which changed his life and changed the whole connection of logic and technology forever. This is a modern reconstruction project for the Turing's bomb, and that's the machine which was the workhorse that broke the Enigma messages day after day throughout the Second World War. This machine carries out one particular procedure with some variable input, the different messages that you could use it for. And so it's like a modern-day computer program. It's not a computer, it's like a program or an application. And so in a way, you could say Turing's computer ideas were motivated by the idea that instead of building very difficult, elaborate machines like this, you'd have one machine, which we're now familiar with, it's the computer, and then you write new software for it.
Manchester University, where anyone who urgently wishes to know whether 2 to the power of 127 minus 1 is a prime number or not, can be given the answer by an electronic brain in 25 minutes instead of by a human brain in 6 months.
Alan Turing was very keen on the viewpoint that whatever the brain was doing, it must be something that was done by some definite process. It worked in some definite way. And therefore, there's no reason why that definite process couldn't be encoded as some form of a program, and if it can be encoded as some form of program, it can be run on a computer. Faculties like originality, creativeness, initiative, and so forth, that those are actually mechanical, those things which could be programmed. Alan Turing's test is this. You have a computer-based system which is trying to show off its intelligence. And to test that, you have another person, ordinary person, and the impartial judge has to receive both the messages, both from the computer and from the human being, and is to conduct a conversation. And it's meant to be any kind of conversation. It's not just meant to be a conversation about sums or about computer-like things. And the judge has to come to a decision as to which is which. And Turing's argument is that if the judge cannot tell which is which, then we should credit the machine with the same kind of intelligence as is being credited to the unseen human being.
So Alan Turing bequeathed us the Turing Test, which seems to say that if a machine can communicate like a human, it thinks like a human. Now, I know lots of people have tried to program computers to pass a Turing test, and they've all failed fairly dismally. Kerstin, what's so tough about what's so tough for a computer to communicate with a human in a realistic way?
It is because in real communication among human beings and also other animals, some things are simply simplified. For instance, often the meaning of a certain symbol is very ambiguous, but it is solved by two human beings sharing a common context, and this is often helping, and this is simplifying the computational power that you need in order to figure out what is going on. For instance, if I say to you, this glass, then do you have a problem figuring out which glass I mean? Well, maybe there's a slight ambiguity. Maybe it's this glass, or maybe it's Mark's glass.
Yeah,
but it's
I know that if you're going to ask me about
but I mean,
glass, it's going to
basically,
be my glass.
you know that I
else.
don't mean the glass standing over there. For a computer, say, who has no way in recognizing my gestures, who is not sitting where you are sitting, I could basically mean any glass, and I would have to specify that my gesture, is a reference to this glass. So what I'm saying is that the Turing test is indeed tackling a very, very hard problem, which in real life isn't that much a hard problem, because there are many ways of verbal, inverbal and non-verbal communication of two embodied systems sharing a common context that simplify the problem. So for me, the Turing test is certainly interesting, but it is focusing on the wrong things. This is maybe why it's so hard.
So, well,
No, I would say it's not just the shared context, because we type email back and forth all the time. It's that we share common sense. We have a vast amount of knowledge that we all bring to bear to understanding the simplest sentences. Two sentences, for instance. Yeah. Simon was hungry. He went to the store. He saw an apple on the shelf and he bought it. How do you know he bought the apple and not the shelf or the store? We know. We have common sense about what food is and so forth, and we don't have to be in the same room pointing and so forth to share that.
Apart from the sheer technical difficulty of getting a machine to pass the Turing test, that's a problem which has proved to be a lot more complicated than I certainly think Turing imagined it would be. There's the actual validity of the test itself, and I don't really buy into this what seems to me very, very simply behaviouristic test for understanding. What Turing seems to be saying is something looks like a duck, walks like a duck, quacks like a duck, and sure as hell that is a duck. And it obviously quite patently isn't. You can imagine watching, for example, a duck on a in the cinema on a screen. That's not a duck you're looking at, that's a representation of a duck. Or a little toy that waddles across a table, that's not a duck, it's a toy duck. And just because something shares certain attributes in something, you can't say it's a duplicate of something else. So for me, the Turing test is a product of its time. Turing came out against the backdrop of the logical behaviourists philosophically, and he wanted a test that you could give a definite yes or no answer. Does this thing understand, does it not? In a very testable kind of way. Has it got intelligence, has it not? But I find the test myself just too behaviouristic, and we've got to move on from that.
The important thing, I think, about the Turing test in its time was the concept that thought might be mechanised, that it might take a very different form from our own, and that indeed we might be able to design such things. That was the crucial insight, that it might be possible to do these things. The way that the test was designed at that time was around what he thought would be the hardest thing to do, i.e. those things that we find hard, like solving differential equations and so forth, which are these advanced symbol processing things. Time has shown us that those are the easy things to mechanise. But the hard thing to mechanise is the interaction of that symbol processing system with the physical environment in which it finds itself and its own physical reality. We also know psychologically and neuropsychologically that language, although it contributes something important to our mental skills, is by no means the be-all and end-all of those skills.
Well, what
People
other
who are
tests would
severely
you...
aphasic, for example,
Right.
are perfectly able to play chess, navigate through complex environments, carry out their own human relations. Their family life doesn't fall apart.
But they communicate in the other ways that Kerstin was talking about earlier.
Showing that the linguistic form
Right.
of communication that is specifically developed in humans is just one aspect of this complex society of experts that we have in our
What
heads.
other tests would you advise then? I mean, we talked about chess earlier. I remember people used to talk about chess as being the fruit fly of artificial intelligence. It's what, in the same way as geneticists test themselves against fruit flies, AI people used to do it against chess. Chess has been cracked. Communication we don't like for various philosophical and other reasons. What would you offer as a test?
Well, there are many problems that people in the field call AI complete, that if you could solve this one, you'd basically be able to solve a lot of others. For instance, have a system summarize a movie by watching it, knowing the character, first of all, recognizing the characters.
I find that quite difficult in some films. Personally.
Well, it's very difficult, especially 2001. And so you'd have to recognize objects, their relationships, motivations, things off screen that you don't see, understand the motivations of the individuals. It's a profoundly hard problem. It's going to be a long time before we can
You'd be
solve
happy with that?
I would be very happy.
Other people would accept that as a decent alternative?
I'm not particularly enamored of the idea of a test. And it's such a complex thing. Cognitive systems that can acquire and manipulate knowledge, and there are so many ways of doing it. That asking for a test of whether they're doing it in an okay way is asking, like, give me a test for whether something's beautiful, and I'll subject anything to this test, and I will decide whether it's beautiful or not. Well, beauty isn't a thing of that nature.
I like it because it helps focus research and allows you to gauge some sort of progress. It might not be progress on the full problem, and just as I think Deep Blue shows, that it's not cracking the problem of intelligence. Nevertheless, I like tests.
Oh, I like steps on the way. Sure, absolutely fine.
Kerstin.
I think one of the problems is also not to have a test. I like tests too. I think that all of us agree with it. My particular problem with, for instance, something like the Turing test or deciding on a test you suggest is to say this is the test. This is the standard reference test. If you're interested in intelligence, also on an individual level, also from an evolutionary level, then you can think about a set of tests. For instance, what about an intelligence test for a 1-year-old child? What about an intelligence test for dogs? For dogs, smell is very important. So surely the test in that case had to include something like distinguishing maybe or finding objects somewhere or other mates, you know. So I like to think more as since intelligence, as I think all of us agree, is nothing you can formally define and say, okay, and this is intelligence and there's one test for that, and then either you can pass it or not. Thinking about tests of intelligence, so different types of tests which can also account for the complexity and different facets of animal systems in general and human beings.
One of the qualities you mentioned early on was let's have different tests for different things. Let's imagine we had a test for emotions. How would we? Is there any test that you've thought of that would tackle that?
I mean, for social intelligence, one of the things I'm usually very amazed by is how, say, people working in a hotel as a receptionist, they get to deal with upset human beings every day on a regular basis, and their primary job, I mean, sure, they need a lot of knowledge, just knowledge, how to do things. This is one aspect. The other aspect is keeping people happy, talking to them, trying to calm them down is very, very hard. Very, very hard. And surely you can have at many hotels have a kind of interface where you can automatically check in or check out. This is not what I'm talking about. But I'm talking about having an upset customer coming to the receptionist, and the receptionist has to find a solution. So that afterwards, after the conversation is over, everybody is happy and the customer returns to the hotel.
But I've
seen
very
difficult.
computers that have been programmed to try and pass a version of the Turing test, and that's a sort of thing they seem to be able to do, is to chat to people and calm them down, or there's a psychiatrist Turing test program. So that seems to be not so hard.
No, it is. Try it. It is very, very hard. I mean, part of how you deal with other people is that you have to bring in your personality and the way you, in particular, not a human being in general, deals with other people. I mean, if you use something like an ELIZA system, and I've tried it out.
So ELIZA was the psychiatrist.
Yeah, where you just type in little questions or so. This might maybe in certain contexts be a kind of therapeutic tool, like using any kind of tool, but this is not the kind of system that you could build a relationship with.
Okay, so it's easier to be a psychiatrist than it is to be a hotel receptionist. Is that what you're saying?
It is certainly easier asking some more or less random questions. Tell me about your mother now and then. This is relatively easy.
I saw a version of this where you, whenever you mention the word father, it says, tell me about your father. But when you say Nelson Mandela is the father of the nation, it also says, tell me about your father. Yeah. So it's obviously not the smartest machine in the world. We've talked about tests, and we've talked about lots of tests, and I suppose that's a way of avoiding the real issue, which is how do you actually build one of these artificial intelligence machines. Well, Martin Smith is lecturer in robotics at the University of East London. Here's his view of a strategy known as the bottom-up approach.
It's not going to be possible to program everything into a machine that a human being knows. That would just take so many years of hard, grinding programming. We need to make a machine that can learn by itself. If we follow the bottom-up approach, looking at very simple machines that mimic very simple animals, very simple single-celled organisms like an amoeba, and try and duplicate that, and then try and duplicate the next level organism up until eventually you're duplicating a worm, and then duplicating a slug, and then a cat and a dog, and then eventually a monkey and a human, and so forth. Building machines that are gradually getting more and more intelligent, copying evolution, following evolution. And we know, because it's worked before, that provided we can copy it, we can make it work again. These little creatures are about as simple as you can get. So these are electronic equivalents of an amoeba. So some are light following, some will avoid obstacles with their whiskers, some will just move at random, avoiding too much light, too much dark, and areas where they're liable to bump into things. So they're more or less equivalent electronically to amoeba. Then if we move up the evolutionary tree, this machine is a learning machine, so it will move its legs at random, and after a while it will remember those leg movements which are useful, which make it walk forward, forget all the leg movements that weren't of any use, and when it does that, it will have taught itself to walk. This machine learns by itself. It doesn't need any program. It has no program. These machines are very much the first step in intelligence. In fact, they have no real intelligence at all. They are just responding to their senses, to their environment. Intelligence is an emergent property from complexity. So if you make a complex enough machine, it can become intelligent, and vice versa. You can't have intelligence without a complex machine. You need all that complexity. You need as much complexity as you can possibly get.
In the film, Martin Smith talked about the bottom-up approach. I'll come back to that in a second, but I assume that there's also a top-down approach, and no doubt the top-downers hate the bottom-uppers and vice versa. Perhaps we should give the top-downers a fair chance. Are there any top-downers here? Anyone who'd like to explain the top-down position?
I'm happy to explain it, but I think we'll need both. In top-down systems, I think a good example would be the Psych project in Texas at PsyCorp, where in order to get common sense about the world, individual knowledge engineers are typing in facts about the world. When you're dead, you stay dead. Animals run faster forward than sideways. This is very high-level knowledge that we all share, and that is put in, and they've spent 500 person years.
So the top-down approach means you start at the top by feeding it
high-level concepts and conceptual relationships, and not having it have to learn it explicitly from lots and lots of low-level experience.
So is everybody here anti-top-down? Is anybody?
No.
Oh, okay. I mean, what's the advantage of that? How far the top-down has got?
Oh, a lot has been done. I mean, Deep Blue for a start.
Yeah.
Another advantage of top-down approach is that you can usually you can ask it why, the system why it decided to do things in a certain way. And I'm more involved in what's colloquially called the bottom-up approach to I myself, but one of the advantages if you're going to use a computer system in control of a nuclear power station or in a medical system, you can get a reason for why it chooses to act in a particular way. That's perceived to be good.
Okay, so if I'm going to build a top-down approach, if I'm going to build a top-down system or I'm going to build an expert system, I just tell it everything it needs to do.
Give it lots and lots of knowledge, lots and lots of rules for manipulating that knowledge.
And it works in many circumstances, but where's the flaw then?
It's often very brittle. It does not have enough information for special cases. If you throw something quite unusual at it, it breaks much more drastically than some of these bottom-up systems. These bottom-up systems may have learned to crawl on gravel, but now if they are asked to crawl on ice, they don't do that badly. So they perhaps can generalize better.
So what's the fun? Okay, so what's the? Perhaps somebody could reiterate the bottom-up approach for me.
Well, one of
in a certain way, you can also talk about the distinction bottom-up, top-down, not necessarily what kind of mechanisms do you use, whether neural networks or rules or whatever.
Okay, neural network. What's a neural net? How's that going to work?
Well, I mean, I don't know how detailed this should be explained.
I'm happy to talk about neural nets.
Go for it, David.
Neural nets were based loosely on biological neurons, which are very simple nonlinear systems, and the power comes from having a very large number of them and the interconnections between them. What we've learned over the last several decades is that the biological inspiration is really not all that important. It's the fact that they're learning and they're basically doing statistical estimation, statistical learning. And that's very useful for a wide range of problems.
I would have to come in. I mean, I work with neural networks, and that's my main 9 to 5 part of what I do in my job. But I'm really alarmed when people say, and it's a very common thing to say, that neural networks learn, because I'm not convinced that they do. If I, for example, have a black box, a neural network, and I try to teach it, for example, the +2 operator, I might give my neural network an input of 2 and tell it that the desired output's 4. Give it an input of 3, tell it the desired output's 5. Give it an input of 66, tell it the desired output's 68.
And what's it doing in the meantime?
You're giving it lots and lots of desired input patterns, lots and lots of input patterns, and lots of target output patterns. Now the idea is if we do that often enough, over a reasonable range of input conditions, the neural network will, in quotes, learn the +2 operator. But we can quite patently see that it doesn't. If my training data is over the range 0 to 100, and I give the neural network 517, it might give me any number as the output, it might give me 521. Whereas I believe that you do understand what is meant by adding 2. But I could give you any number and you would correctly give me the +2. And I just don't think that we use the word learn correctly.
Well, I profoundly disagree as head of the machine learning and perception group at RICO Innovations. Learning is changing your behavior based on input and output. You can choose problems such as long division, for which neural networks are terrible systems and will not generalize well, but there are many problems for which they do. Handwriting recognition, speech recognition, and so forth. All these things, the fundamental thing is learning is changing your behavior based on input and output.
That's your definition of learning, but if we were to ask somebody outside the Science Museum today what they mean by learning, I think they wouldn't necessarily define learning in terms of adjusting of synaptic connections.
No, it doesn't have to be synaptic connections, and I don't say it has to be synaptic. And you can have grammatical learning. Yeah. You can give it examples of noun, verbs, and objects and so forth, and have it learn patterns of sentence structures. So the key thing in learning, not neural network or statistical or grammatical, a whole range, is you're changing your behavior based on input and desired output.
Martin Smith mentioned a point in the film. He talked about something called emergence or emergent properties and complexity. What did he mean by that?
Yeah. I mean, I think if you look at the way how people design systems, say you want to have a robot that can navigate from this room to a room in the next building, then there are 2 ways how you can do it. If this is a problem where you can clearly specify, and also formalize how this can be solved, say you want to use a particular navigation algorithm and you're happy if this algorithm is applied, then it actually doesn't matter, say, for instance, whether you use neural networks or evolutionary techniques. You can specify the problem and you can then bring it down to your particular implementation and then you can test it. What, for instance, people interested in emergent behavior, artificial life is another, which is, I mean, the field of A-life is related to artificial intelligence, but I mean, there's overlap, but it's not the same. People are more following an incremental, or you might call it developmental approach. What they are saying is this robot that should navigate, you start with the robot doing something very, very simple, just moving forwards, covering some ground, then something a bit more difficult, like avoiding obstacles, moving around a corner. So slowly you're building up levels, and at each stage you are implementing it, you are testing it, you are evaluating it, and then you decide what comes next. And what you can often discover is that that you can observe behaviors that are emergence, in the sense that it is nowhere specified explicitly in the program how this behavior is coded. This is then what people call the emergent effect. So there's no explicit behavior or there's no explicit representation of the behavior.
So that's where the complexity comes in.
Exactly. People are hoping to build more and more complex systems where more and more behaviors interact with each other, and what is very important, interact with the environment. We're not talking about a static system. We're talking about a system that is doing something in the world that gets feedback.
This makes me think of the internet. It starts off as simple, it's just connections, it's interacting with the outside world, it gets bigger and bigger and bigger. Weird ideas. Could intelligence emerge out of something like the internet?
I think we are at a very interesting time in the history of thinking about intelligence. There have been several models of how intelligence can be built or modeled, and Descartes talked about tubes and so forth. Then we had the model of the telephone switchboard, and then for a long time there was the mainframe computer, HAL, and then there were individual robots like David in the film AI, and I think we're moving to an era where the internet could be the locus of the development of AI. There are many reasons for it. First of all, the architecture is somewhat like it, very informally like the brain, in that there's no central controller. It's very diffuse. There are very faulty systems that contain flawed and broken information that is inconsistent. But I think the single most important aspect about the development of AI in the internet is that there's a financial incentive. People aren't going to build a HAL to fly a spaceship to Jupiter, but people are going to want intelligent search, summarization of information, and so forth. And these systems, we also have the ability to compare my search engine versus your search engine. So there's a real economic drive.
But you're saying there that the internet isn't the thing that's executing the intelligence, it's embedding the intelligence. It's an arena by which we can test our AI programs.
Partly, yeah, but also that they will come back with solutions that no one individually programmed in. We'll get answers that no one could have expected.
But the intelligence in our own brain may not be in one bit. It's in the whole system.
Sure.
And so the internet is a means for enhancing the capabilities of the whole society, the whole community that uses it.
Yeah.
It's a means for knowledge creation, in a way.
But before we leave the Turing test and the top-down approach, I think it's important to stress that one limitation of systems that just shuffle symbols or manipulate symbols in very clever ways is giving meaning to these symbols. And this is Searle's Chinese room argument, that he was saying in an analogy that if you were shuffling Chinese symbols, you might be able to do it in such a way as to shuffle them appropriately, learning how they were related in Chinese scripts. But if you never saw these things related to the world or never knew how they were related to the world, couldn't give them meaning, then you're lacking something absolutely essential. And I do think that this is the case, that no matter how clever the symbol manipulation systems can be, unless they can give those symbols a meaning in a universe of existence outside of themselves, then they won't be using them as symbols in the way that we do. And I think the main way, an important route to giving symbols meaning is by embodying intelligence within an environment, including other ones, social environment of other animals, or interacting with humans, but in a way that it's interacting with the real world outside of the symbols.
And I don't think embodiment per se is enough to guarantee understanding. You've got to, or somebody who is interested in this has got to tell me what the mechanism is where we will get this understanding.
Absolutely, and I think it's a really crucial issue, this, and I think it's one that's not solved in neurobiology, let alone in AI, that we don't know how it is that brain signals can mean something to other bits of the brain.
But I know
they are, you can think of them as symbols, and that although we sit here now experiencing what we think to be the external world, we all realise that our own conscious awarenesses that we're now having are taking place in our own heads, and we have every reason to suppose that what's happening in our own heads are firing of neurons which in and of themselves are as distantly related as any arbitrary symbol to what's actually going on in the real world. There isn't a red signal in my head when I see red.
Okay, so maybe this takes us onto the next. I mean, so far we've been talking about nuts and bolts intelligence, and maybe we should move on to ideas of creativity and self-awareness and imagination. In terms of creativity, what I'd like to do is just do a little test here. I'm going to play you a couple pieces of music, and then we'll just see what you think of them. Here's the first clip. Okay, that was the first clip, and here comes the second. Any connoisseurs of music? Anybody like to?
I'm a serious musician.
What did you think?
The second was computer generated and the first was not.
Would everybody agree with that?
My guess was that the second one was computed by a program that listened to a lot of Mozart, tried to extract the structure, recognise the pattern in Mozart, and then recreate it.
I think you're probably right. The second one was composed by a program called Experiments in Musical Intelligence, which in turn was composed by a chap called Dave Cope at the University of California. Was the second piece of music, or was the computer that created it in any way creative by any definition of that word?
I would argue that that the program itself wasn't creative. The act of creativity lies in the skill and ingenuity of the programmers, or the programmer in this case, aided by very, very sophisticated piece of electronic machinery, a computer, to instantiate his thoughts at very rapid speed, enabling him to do things that without the computer he wouldn't be able to do. So he's defined a new means of composing music. But by the use of a computer following his set of rules, he's able to create bits of music that sound to the uninitiated vaguely musical, albeit without a bass beat behind it.
I mean, do you think it would ever be possible to hear a piece of music and for you to give it the credit of being creative in terms of that's what a computer created and it's original? Or would you always credit the right of the program?
Well, as you can probably guess from my pronouncements on this discussion so far,
surprise me.
I'm sceptical when people claim of a mechanical clockwork-like system that such a system is creative.
I think I'm fighting an uphill battle here, but I'm going to try again. Here's another example of creativity. It's a program called Aaron, written by the artist Harold Cohen, and let's see if you find this a little more impressive.
It will make paintings of anything it knows about. It knows actually relatively little about relatively few things. It knows about human beings, it knows how to grow plants, it knows how to make boxes and pots and things like that. But then it has another body of knowledge about how to build that knowledge into a representation. That's a completely separate issue, which is quite unlike any of the computer graphics ways of going about things. The most challenging thing by far has been coloring. Human beings who function as colorists are making use of their eyes, a very powerful feedback system. A computer can't do that, at least my one can't, because it doesn't have eyes. The program composes the entire thing before it ever starts putting the colors down. Seems to work fine. It's simply an alternative way of going about things. But it took me a very long time to get my head in the right place before I could see that. I do not think that my program is creative. I seem to have much more stringent notions about what you mean by creativity than most people do. A test I proposed some years ago was that if I could stop working on the program in January and in August it produced images it could not have produced in January, I'll be prepared to say that it's a creative program. I'm not simply talking about having the program randomly change its parameters so it comes up with different images. I'm talking about intelligent self-modification. I think that's a goal, and I think it's an article of faith that we're going to get there, but I'm quite clear that in my own mind that Aaron is not. The idea that it doesn't know what it's doing, it's simply following rules or something, well, you know, in the first place, I'm not sure to what degree artists, human artists, know what they're doing. It's never clear to what extent they're following rules either. It's just that the rules become more complex and you can't keep track of what's going on. When one uses terms like that, one is thinking in terms of human beings. One is aware of what one is doing. Is the computer aware? I haven't the faintest idea. I don't know how to ask the question. But I don't think any entity could do anything this complex unless it knew what it was doing.
I'm going to ask you this anyway for the hell of it. Any sympathy with that at all?
No, I mean, I think it's clear from my earlier pronouncements, I don't think that that program knew anything at all. If it knows anything at all, it's how to load a number from its memory into its accumulator and add another number to it as it executes the machine code of the program that controls the robot that draws the pictures. That's the most knowledge I'm prepared to give that program.
Kerstin, I know you have an interest in these robots that are almost brought up. They're sort of almost born and then they run around the world, they bump into things, maybe they experience the early signs of what we might call pain. Do you think any of those robots could ever be creative in the sense that Harold Cohen's trying to suggest?
I think no robots that I will see in the next 10 years. What I would expect for a system to be truly creative is to have a personality and to have a life. All robots that I know at present, you switch them off at the end of the day and this is it.
They don't scream.
Yeah.
Discussion of the issues of creativity, what underlies that is a concern for asking, are there things that we can do that machine intelligence in principle can't? And I think that there is one thing that no matter how long we wait, and that no matter how clever or fast they become, they'll never be as good at us at, and that's being human. To be human means to have a particular physical reality and a particular personal history that you know about, and to have a sense of self, that you distinguish yourself from the outside world. I think the most important thing about the statement that Hal made when he said, sorry, I can't do that, was the simple word I. And to have a sense of self requires things which are not on the horizon, as far as I know, in any machine intelligence yet.
That seems to be sympathetic with what you're saying, Mark. You're happy?
Yeah, I've got some sympathy with that. I mean, my fundamental concern about AI, in the sense of that sort of stops me worrying too much about machines taking over the world, which is a prophecy I've heard once or twice, is the fact that I don't think, it isn't clear to me that the mere execution of a computer program is enough in of itself to instantiate phenomenal states. And what I mean by phenomenal states are the sensation I would get if I biffed you on the head, or if I look
I didn't flinch there, did you notice?
That's pretty impressive.
I just wanted that to be acknowledged.
Or if I look at the particular blue of your shirt. And it isn't clear to me how the execution of any computer program can instantiate such states in a machine. And unless you have phenomenology embedded in the machine, then it isn't clear to me how you can ground the machine in the world in which we live.
I'm not sure you need phenomenology, but my main point would be, though, it's easy to talk like this now when computers are so stupid. It's going to be much harder 100, 200, 500, 1,000 years from now, when the other side of this conversation is being held up by a computer. It really does say, yes, I do see blue, and it really does flinch and so forth. I think it's way far away, much longer than many other prognosticators. I agree that there'll be useful tools and so forth, but I think another reason to build AI is to understand ourselves. There's so many problems that we didn't realize humans were solving until we tried to build them into machines.
Absolutely.
My favorite example is segmentation in speech. we hear individual words when I'm speaking, but there's no such demarcation in the sound itself. And it's only when you try to build a machine to recognize continuous speech that you realize this amazing thing that we do. And so we understand ourselves better. And what really excites me is that I feel confident that there are other profound problems that we don't even realize now.
Okay, where are we going to be in 50 years' time, Mark?
I think we'll have machines that will be even better at passing tests like the Turing test that we discussed earlier on. I think we'll have.
Do you think we'll pass a Turing test within 50 years?
I'd be surprised, but I think the programs will obviously improve. They'll get better. We'll have robots that'll be more ubiquitous. They'll be more sophisticated. We'll have more insight into the way that human mind works from our investigations.
I want something concrete. I don't want more or better. I want a new toy to play with.
Well, I mean, what I would wish that we have is systems that can make us laugh, that can tell us really funny stories, not just, you know, some short stories or trivial cases, but systems that can make us laugh, that can entertain us.
So a sense of humour.
Humor is
indicates subtle intelligence of emotions and understanding the outside world and so on.
Yeah, I mean, surely you can say you can tell short jokes, you know, some simple jokes which are maybe based on different interpretations of words. This is not what I mean. What I mean is, for instance, robots that can tell us about their experiences, and we can relate to these experiences, and they can realize that we can relate to them, so they can modify the kind of stories that they tell us.
Okay, robots with a sense of irony or self-deprecating
Yeah,
humor.
exactly.
Okay, you said that's what you'd wish for.
That's what I wish for.
Will it
I am
happen?
actually very pessimistic about that. 50 years is too soon.
Okay, so the odd knock joke, but not much more. Okay.
I think people will become more used to interacting with other kinds of intelligences.
Yeah.
Just as when humans from the West met people from very other communities, they found that the human species could be very much more various than they had previously imagined. And it expands our consciousness. And I think that we will, in 50 years' time, not us, our grandchildren will grow up used to interacting with capable knowledge-based systems in ways that we're not used to. In fact, it's already happening.
Do you think the film 2001 genuinely inspired interest in research in AI? I think your own
Absolutely.
career is lip reading, which is one of the things that appears in 2001. Will the film AI kickstart artificial intelligence, or is it already a thriving industry?
So it's thriving.
We could go through the long history of AI. I think having a vision often helps. It can mislead. I think in some senses the Turing test misled the field into trying to address very high-level problems when crawling across the ground is maybe our first step, should have been our first steps. But we are going to be inspired by these films, and AI, will become, more a part of society.
Okay, well maybe that's a good place to stop. Thank you to my guests, David Stork, Mark Bishop, Bill Phillips and Kerstin Dautenhahn. Before we finish, perhaps I could just leave you with a little story that I've heard from a couple of AI researchers, and it concerns the year 2050. Imagine, if you will, that the AI community unites and interconnects every computer in the world in an almighty effort to create true machine intelligence. They try a bit of top-down, a bit of bottom-up, they allow a few neural nets into it and so on, and allow it to stew for a decade or so until they've achieved true intelligence. And at that point, the chief programmer goes up to the computer and asks it the ultimate question: is there a God? There's a short pause, and then the computer replies, there is a God, now. Goodbye, don't have nightmares.